The universe breathes. Its galaxies drift apart like glowing embers carried by an invisible wind, scattering into an ever-widening darkness. From every direction, space stretches, as though reality itself is exhaling. A slow, endless expansion that has been unfolding for nearly 14 billion years. And yet, this vision hides a haunting paradox. If the universe is everything, all of space, all of time, all that has ever existed, what does it mean for it to expand? Into what does it grow, if there is no outside for it to fill? Imagine standing at the very edge of existence, beyond the farthest galaxy, beyond the last photon still racing through the void. Ahead lies not empty space, but something stranger, a place where even space and time themselves vanish, where distance has no meaning, where there is no beyond to cross into. The cosmos is like a canvas that paints itself while you watch, an infinite mural without a frame. It is like a balloon that swells but finds no air around it, like a dream that deepens with no sleeper to awaken. Every moment of expansion is not a movement outward, but a rewriting of reality itself. More space, more time, more possibility. So what are we really watching when we say the universe expands? Is this a story of growth into nothing, or a story of existence creating more of itself, pulling us with it into a future as vast and mysterious as the question itself? If you are new here, join the journey. Like, subscribe, and let's begin. For centuries, the night sky seemed eternal. The stars above appeared fixed, motionless, burning in their places since time immemorial. To the human mind, this quiet perfection suggested a universe without change, an infinite stage, stretching forever, timeless and still. Even the greatest thinkers of the past, Aristotle, Newton, imagined a cosmos that simply was, existing in a steady state, without birth and without end. When Albert Einstein formulated general relativity in 1915, he too imagined that the equations must describe a universe in balance, a cosmos neither collapsing nor exploding, but his own mathematics seemed to betray him. The solutions predicted something dynamic, a universe in motion, either contracting or expanding under the weight of its own gravity. Troubled by the implications, Einstein added a term to his equations, the cosmological constant, a delicate mathematical adjustment meant to counteract gravity and hold the cosmos still. With this single symbol, he froze the universe in place. For a brief moment, it seemed that theory and intuition were reconciled. The cosmos was eternal once more, or so it seemed. But far from the quiet study rooms of Berlin, high atop Mount Wilson Observatory in California, a man named Edwin Hubble was watching the sky with a new kind of precision. Through the 100-inch Hooker telescope, then the largest in the world, he observed faint smudges of light known as nebulae. Many astronomers of the time believed these glowing patches were clouds of gas within our own Milky Way, small ornaments within a single, all-encompassing galaxy. Hubble was not convinced. He began meticulously photographing these nebulae, searching them for Cepheid variable stars, stars whose rhythmic pulsations allowed astronomers to measure their distances with remarkable accuracy. What he found was revolutionary. These nebulae were not nearby clouds of dust. They were entire island universes, separate galaxies, and they were far, far beyond the Milky Way. But the true shock came when Hubble compared their distances to the spectral lines in their light. The lines were shifted toward the red end of the spectrum, stretched as though the light itself had been pulled apart on its journey through space. The farther the galaxy, the greater its redshift. This was no ordinary motion. It was not as though these galaxies were flying through space like shrapnel from an explosion. Rather, the very fabric of space between them was stretching, carrying the galaxies away from one another. The relationship was precise, almost elegant. Distance was proportional to velocity. In 1929, Hubble published his results, and the static universe died. The sky was no longer a silent cathedral of fixed stars. It was a living, breathing, changing thing. The universe was expanding. The implications were staggering. If the universe was expanding now, then in the past it must have been smaller, denser, hotter. Push the clock backward far enough, and one would arrive at a moment when everything, every galaxy, every star, every atom, was compressed into a single, unimaginable point. The idea was almost too strange to believe. Some astronomers resisted it fiercely, preferring to imagine new forces that might maintain a steady-state cosmos. Even Einstein, upon hearing of Hubble's work, is said to have admitted that his cosmological constant was the greatest blunder of his career. But there were minds ready to embrace the idea of a universe with a beginning. One of them was a Belgian priest and physicist named Georges Lemaitre. Drawing on Einstein's equations before Hubble's discovery, Lemaitre had already proposed that the universe was expanding. Now, with Hubble's data as evidence, he went further. Lemaitre imagined that all of creation began as a single, primordial quantum, a primeval atom containing the entire mass energy of the cosmos in a state beyond comprehension. He called it the cosmic egg, exploding at the moment of creation and giving rise to space, time, and everything within them. This was not merely a scientific idea, it was a reimagining of reality itself. The universe was not an infinite, unchanging ocean. It was a story, one with a first chapter, one that was unfolding in time. The discovery rippled across physics like a shockwave. The steady-state comfort of an eternal cosmos was gone, replaced with something more dynamic, more mysterious, perhaps even more unsettling. For if the universe had a beginning, what determined its birth? And if it is still expanding, what is it expanding into? Astronomy, once the study of eternal motions, had become the study of cosmic history. Humanity was no longer looking merely at the stars. It was looking backward in time, toward the moment when time itself began. This was the dawn of modern cosmology, and it reframed every question we could ask about existence. If the universe had a birth, might it also have a death? If it has a shape, what is its edge? And if it grows, what does it mean to grow when there is nothing outside? The revelation struck like a silent thunderclap. The galaxies were not merely rushing apart as though cast outward from some distant explosion. The very stage on which they moved, the cosmic fabric itself, was stretching, pulling everything with it. It was a truth that defied intuition. Human experience had prepared the mind for a different kind of motion, one where objects traveled through a pre-existing space, like stones skipping across a pond, or planets tracing ellipses around the sun. But Hubble's discovery suggested something more profound. Space was not a static container holding the contents of the universe. Space was dynamic. It was growing, weaving more of itself from moment to moment. This was not an ordinary explosion. There was no center from which debris was flung, no empty void waiting to be filled. The galaxies were not racing through space. They were carried along as space itself swelled between them. This was the first great shock of modern cosmology. It demanded a radical reimagining of reality, one in which the familiar intuition of into what no longer applied. When a balloon expands, it grows into the air around it. When a ripple spreads across water, it moves outward across a larger surface. But the universe was not expanding into anything. It was simply expanding. This realization carried with it a haunting question. If the universe is growing, what lies beyond its edge? And if there is nothing beyond, how can it grow at all? The mind strains at this paradox, because it has never encountered anything like it. Physicists began to grapple with the concept of a finite but unbounded cosmos, a space that might be curved, like the surface of a sphere. Imagine walking in a single direction across the Earth. Eventually, the traveler returns to the starting point without ever finding a boundary or stepping off an edge. Such a surface is finite, yet it has no border. Einstein's equations allowed for just such a geometry in 3 dimensions. A cosmos that could be finite in volume yet endless in travel, with no outside into which it must expand. This image was as beautiful as it was unsettling. The universe might be like a sphere, not in ordinary 3-dimensional space, but in a higher mathematical sense, curving back upon itself. In such a cosmos, expansion does not mean swelling into an empty void, but rather a stretching of the very metric that defines distance. Every point moves away from every other point, not because there is a destination, but because the meaning of distance itself is being rewritten at every moment. This was a revelation that forced physicists and philosophers alike to confront the limits of language. The words outside and beyond lose meaning when applied to the totality of existence. There is no external vantage point from which to watch the universe grow, no arena into which it spills. Expansion is not a journey, but a transformation, an ongoing rewriting of reality's stage. the strangeness deepened when cosmologists considered the implications for time itself. If space could grow, could time also stretch? The equations suggested that it did. The expansion of space was inseparable from the flow of time. A dynamic universe was not merely changing its shape, it was changing its age, dragging every atom forward into new moments that had not existed before. This reframing of the cosmos shattered the last remnants of the classical, eternal view. There was no steady background, no fixed scaffolding. Everything was in flux. Space was an actor, not merely a stage. It could bend, ripple, grow, and perhaps someday collapse. To a civilization that had imagined the stars as eternal lanterns, this was a disorienting truth. It suggested that the universe itself had once been smaller, denser, hotter, that it had a beginning, and if it had a beginning, perhaps it might one day have an end. This was not just science. It was a philosophical upheaval, a shift in the human narrative. No longer could the universe be seen as an infinite, unchanging cathedral. It was a living story, a process unfolding in time, and somewhere within that story, the question remained, whispering like an echo from beyond comprehension. If there is no outside, where is this universe going? The idea of an expanding universe was no longer a philosophical curiosity. It was a prediction that demanded evidence, a trail back to the universe's earliest moments. If the cosmos was once smaller, denser, and hotter, then some echo of that primal fire should remain, still whispering across the heavens. That whisper was found by accident. In 1965, two young radio astronomers, Arno Penzias and Robert Wilson, were calibrating a large horn-shaped antenna in Holmdel, New Jersey. They were not searching for the origin of the universe. They were searching for silence, attempting to measure faint signals from the Milky Way. Yet no matter where they pointed the antenna, they encountered a persistent noise, a faint hiss that would not vanish. It came from every direction, at every hour with perfect uniformity. They even climbed into the antenna to remove nesting pigeons, believing the culprit to be ordinary interference. But the hiss remained. What they had stumbled upon was no local phenomenon. It was the afterglow of creation itself. The cosmic microwave background, the cooled light left over from a time when the universe was a furnace of plasma. This light had traveled for nearly 14 billion years, stretched by the expansion of space into the microwave part of the spectrum. It was the oldest thing humanity had ever seen, a snapshot of the cosmos when it was just 380,000 years old. The discovery sent ripples through science. The expanding universe was no longer mere theory, it was history written in radiation. Here was direct evidence that the cosmos had indeed been smaller and hotter, that it had a beginning. Decades later, space missions refined this vision. The COBE satellite in 1992 measured the faint variations in this cosmic background, revealing that the universe was not perfectly smooth, but slightly rippled. These ripples were the seeds from which galaxies and stars would one day grow. MAP followed, painting an even sharper portrait, and then Planck, whose detectors mapped the sky with exquisite precision. These missions revealed the geometry of the cosmos itself. Space is nearly flat, stretched out on scales so vast that its curvature is almost imperceptible. The data showed that only about 5% of the universe is made of ordinary matter, the kind that forms stars, planets, and life. The rest is composed of dark matter and dark energy, invisible ingredients that shape the cosmos from behind the scenes. Together, these measurements told a story of a universe governed by general relativity, a universe where space and time are inseparable, where gravity is not a force pulling on objects, but the bending of space-time itself. Massive bodies curve the fabric, light follows the curves, and the very shape of reality evolves with its contents. But there was still a deeper mystery. If the universe today is smooth on large scales, how did it become that way? What erased any primordial irregularities? The answer came from a bold and radical idea: cosmic inflation. Proposed in the early 1980s, inflation theory suggested that in the tiniest fraction of a second after the Big Bang, the universe underwent an unimaginable growth spurt. Space itself expanded faster than light, swelling from subatomic scales to astronomical size in an instant. In this brief epoch, quantum fluctuations, minute ripples in the quantum fields, were stretched to cosmic dimensions, becoming the scaffolding on which galaxies would later form. Inflation explained the observed uniformity of the cosmic microwave background, smoothing the early universe like a perfectly stretched canvas. It also predicted a flat geometry, precisely what Kobe, W-Map, and Planck would later confirm. The mathematics of this picture were encoded in the Friedmann equations, derived from Einstein's general relativity. These equations do not describe objects moving through space, but the expansion of space itself. They are not paths but scales, telling how the distance between two galaxies grows as time flows forward. To model this, cosmologists use metric tensors, the language of curved spacetime, to calculate how distances stretch, how light is redshifted, how horizons grow. The equations reveal a universe whose expansion rate changes with time, governed by the energy density of its contents, radiation, matter, and the mysterious dark energy that now drives its acceleration. The picture that emerges is both elegant and unsettling. The universe is not just a collection of stars and galaxies. It is a dynamical system, a vast solution to Einstein's field equations, evolving according to deep mathematical laws. The stage is not fixed. It breathes. Each observation, each refinement of data added new layers to this cosmic portrait. Humanity was no longer guessing at origins. It was mapping them with the precision of science, uncovering the geometry of reality itself. Yet the deeper the understanding grew, the more haunting the central question became. If space can grow from nothing, what does it mean to say there is nothing outside it? Inflation had erased any trace of what came before, leaving only the universe we inhabit. A cosmos whose edges are not edges at all, but horizons that recede as we chase them. Science had not only confirmed that the universe was expanding, it had revealed the mechanism, the pattern, the very shape of that expansion. A mathematical symphony, cold and beautiful, endlessly unfolding. But the mystery of what lies beyond remained untouched, like a door forever just out of reach. For most of the 20th century, scientists imagined that cosmic expansion would eventually slow. The pull of gravity, acting over billions of years, would work against the outward motion. Perhaps the universe would continue expanding forever, but more gently, with each passing epoch, its motion gradually coasting towards stillness. Or perhaps gravity would one day halt the growth entirely and reverse it, pulling every galaxy back toward a final collapse, a cosmic implosion, a big crunch. But in 1998, a discovery arrived that would upend this picture and shatter the last hopes of a predictable ending. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure how fast the universe's expansion was slowing down. They used Type Ia supernovae as cosmic lighthouses, standard candles so bright they could be seen across billions of light years. These explosions were thought to reveal how much the universe had decelerated since its birth. What they found was the opposite. The galaxies were not slowing their retreat. They were accelerating. The expansion was speeding up. This was not a gentle drift into the future. It was a runaway growth, a silent and unstoppable stretching of the cosmic fabric. Space itself was creating more space at an ever-increasing rate, as though driven by a mysterious pressure from the vacuum. Physicists gave this unknown force a name: dark energy, a placeholder, a symbol for something almost entirely mysterious, something that accounts for nearly 70% of the universe's total energy content. The implications were staggering. The dream of a stable, eternal universe was gone. The vision of a graceful slowdown was gone. Instead, the cosmos seemed destined for endless acceleration, an expansion that would never cease. This deepened the paradox of existence. Space was not only stretching, it was accelerating its own creation, as though reality itself was compelled to widen faster and faster, tearing its own tapestry apart. The effect of this acceleration is subtle today, but relentless over cosmic time. As space expands faster, more distant galaxies cross what is known as the cosmic event horizon, a boundary beyond which their light will never again reach us. Even if one could wait for trillions of years, their photons would never arrive. This means that our observable universe is, in a profound sense, shrinking. Not in size, but in content. The number of galaxies we can ever hope to see is decreasing as cosmic expansion carries them away, faster than light can bridge the growing gulf. If this continues, and every measurement so far suggests that it will, then the distant future will be a lonelier place. The great web of galaxies will thin. One by one, the lights at the edge of time will wink out, Eventually, all that remains visible will be the local group, the small cluster of galaxies gravitationally bound to the Milky Way. Beyond them, the universe will fade to black. To future astronomers, born in an era tens of billions of years from now, the night sky will no longer tell the story of cosmic expansion. There will be no redshifted galaxies to measure, no cosmic microwave background to detect. The evidence of a Big Bang will be erased from their view, hidden forever beyond an unreachable horizon. This is the haunting consequence of a universe with accelerated growth. The more it expands, the less it reveals of itself. The more of itself it creates, the less of itself we can see. The discovery of dark energy was more than a scientific result. It was an existential turning point. It suggested that we live at a special moment, a fleeting window in which the universe is still readable, still illuminated by its own ancient light. In the deep future, that window will close. The question only deepens. What is dark energy? Is it a property of empty space itself, as Einstein's cosmological constant suggested, a quiet tension in the fabric of reality? Or is it something dynamic, something that could change, even vanish or reverse? Could it tear space apart in a catastrophic Big Rip? Or might it eventually decay, ending acceleration and allowing gravity to pull the cosmos back together? For now, there is no final answer. What is clear is that the universe is not coasting gently into its future. It is rushing headlong, accelerating into a destiny that is as strange as it is inevitable. The expansion, once merely a scientific curiosity, has become a cosmic countdown. The farther the horizon recedes, the smaller our island of knowable reality becomes. It is as though the universe itself is vanishing before our eyes, not by collapsing, but by growing too fast to ever be grasped. The discovery of cosmic expansion, and later its acceleration, left humanity standing at the edge of an intellectual abyss. The universe was not static, nor merely drifting outward. It was rushing headlong into something even stranger. The question deepened. If the cosmos is expanding, what exactly is it expanding into? The simplest and most widely accepted framework for describing this mystery is known as the ЛCDM model, lambda cold dark matter. In this standard picture, the universe does not grow into an empty void. Instead, it grows within itself. Space is not expanding into anything beyond it. Rather, the metric of space-time, the mathematical fabric that defines distance, is changing. Galaxies drift apart not because they move through space, but because space itself is stretching, carrying them like leaves on a widening river. This model has been extraordinarily successful, predicting the large-scale structure of the cosmos, the faint ripples of the cosmic microwave background, and the distribution of galaxies we see today. Yet it leaves a profound philosophical unease. If the universe is everything by definition, how can more of it suddenly appear? Some theories dare to step beyond this closed picture, into the possibility that our universe is not the whole of reality, but merely a fragment. One such idea comes from higher dimensional physics, brane cosmology. In these models, inspired by string theory, our entire cosmos may be a three-dimensional brane, a kind of vast, flexible sheet floating in a higher dimensional bulk. What we call the Big Bang may have been the collision of two such branes, an event that filled our universe with matter and radiation and set expansion in motion. If true, then space may be expanding not just within itself, but across this unseen higher dimensional stage. Others take the question even further, imagining an eternally inflating multiverse. In this vision, inflation, the brief, faster-than-light expansion thought to have occurred in the first fraction of a second after the Big Bang, never truly ends. Instead, it continues in the background, spawning bubble universes like foam in a cosmic ocean. Each bubble may have its own physical constants, its own laws, its own birth and death. Our observable cosmos would then be a single bubble, one island among an infinite and growing archipelago. If this is true, then asking what the universe is expanding into becomes a question of what the multiverse itself is. The answer could be that it expands forever, a self-replicating fractal of creation with no edge, no outside, no ultimate boundary. But some thinkers propose an even more radical view, that expansion might not be a physical process at all, but a computational one. In simulation theory, the fabric of space-time could be the result of an underlying algorithm. Expansion could be a feature of the code itself, a way of allocating more memory as the simulation runs forward in time. This is a philosophical speculation, not a physical theory, but it forces a reflection on whether the cosmos is fundamentally mathematical, and whether its growth is simply the unfolding of a program written in the language of logic. There are also quantum perspectives to consider. Some physicists explore the possibility that expansion is an emergent property of the quantum vacuum, the seething sea of virtual particles that blink in and out of existence, even in what we call empty space. Perhaps space itself is continuously boiling new regions into being, a restless process that never stops. In such a picture, the universe does not merely stretch, it recreates itself moment by moment, adding fresh patches of space-time to its own ever-growing map. Each of these models has strengths and weaknesses. The LCDM model is elegant, minimal, and supported by exquisite measurements, yet it cannot say what dark energy actually is. Brain cosmology offers a grander stage, but its extra dimensions remain hidden, untested. The multiverse explains why the laws of physics seem finely tuned for life, yet it risks becoming unfalsifiable, forever beyond observation. Simulation theory is intellectually provocative, but it remains more a thought experiment than a scientific framework. And so the mystery persists. The expansion continues, and with it, our search for understanding. There is something haunting about this pursuit, as though reality has left just enough clues for a curious species to notice that it is being carried along by an invisible tide, but not enough to fully reveal the source of that tide. Every new observation sharpens the picture, yet the frame around it only grows wider. Perhaps the answer will come from a future experiment, a new telescope, or a deeper unification of quantum theory and gravity. Perhaps it will remain forever hidden, an unsolved riddle at the heart of existence. For now, humanity stands in the middle of this vast story, between the fading glow of the Big Bang behind us and the accelerating darkness ahead. The universe expands, and with it, the scope of the unknown. And in that endless widening lies the greatest speculation of all, that the cosmos itself may be not just a place, but a process, a living, growing reality whose expansion is the very act of creation, still unfolding, still writing its next chapter beyond the horizon we can never reach. The quest to understand cosmic expansion did not end with its discovery. It had only begun. For nearly a century, astronomers have built ever more powerful tools, not merely to watch the universe grow, but to measure its very heartbeat. Each new instrument is a window into an earlier, younger cosmos, peeling back layers of time until only the faintest traces of creation remain. At the forefront stands the James Webb Space Telescope, a golden eye stationed far beyond the Moon's orbit, where the Earth's shadow shields it from the Sun. Its mirrors, polished to near perfection, gather ancient light that has traveled more than 13 billion years. Webb's mission is nothing less than to witness the universe's childhood, to see the first galaxies forming, the first stars igniting, and to test whether expansion behaved differently when the cosmos was still a newborn. Its infrared gaze stretches back to an era so distant that space itself was smaller, denser, and brighter, letting scientists reconstruct how the rate of expansion has changed over time. But Webb is not alone. In the coming years, the European Space Agency's Euclid mission will begin its grand survey of the cosmic web, the vast filaments of galaxies that trace the invisible architecture of dark matter. By mapping billions of galaxies across 10 billion light-years of space, Euclid will measure how quickly cosmic structures have grown, and whether dark energy, the mysterious driver of accelerated expansion, has remained constant or evolved over cosmic history. On Earth, the Vera Rubin Observatory in Chile prepares to open its unblinking eye on the night sky. Rubin's legacy. Survey of space and time will capture the entire southern hemisphere's heavens every few nights, building an unprecedented time-lapse of the universe. By watching how galaxies drift apart over billions of years, Rubin will help test whether Einstein's theory of general relativity still holds at the largest scales, or whether gravity itself might need to be rewritten. Beyond these great surveys lies an even more subtle tool: baryon acoustic oscillations. These faint ripples, fossil imprints of sound waves that rang through the hot plasma of the early universe, provide a kind of cosmic ruler. By measuring the apparent size of these ripples in the distribution of galaxies, Scientists can calculate how much the universe has stretched since those waves first froze into place nearly 13.8 billion years ago. With this technique, researchers are pinning down the rate of expansion with exquisite precision, testing whether it is truly uniform across space, or whether some directions might expand faster than others, a possibility that could hint at new physics beyond the standard model of cosmology. Even more ambitious plans are on the horizon. A new generation of gravitational wave observatories, including LISA, a space-based array, could one day listen to the faint tremors of space-time from the universe's earliest moments. Such waves, if detected, might carry information from the era of cosmic inflation, when space is thought to have ballooned faster than light itself. These signals could reveal whether inflation truly occurred, and perhaps even what triggered it. Other telescopes will search for the fingerprints of primordial gravitational waves in the polarization of the cosmic microwave background. Experiments in Antarctica, such as BICEP Array, and future missions in space aim to find these patterns, delicate twists in ancient light that could offer the first direct glimpse of the universe's birth cry. These instruments are not merely machines, they are extensions of human curiosity, tuned to catch whispers from across time. Together, they form a network of cosmic witnesses, each asking the same question in a different way. Is the universe we see the whole story, or is there something more, hidden just beyond the edge of our perception? What they find may shake the foundations of cosmology. If expansion is confirmed to be perfectly uniform, then the ЛCDM model stands stronger than ever. If dark energy is discovered to evolve with time, the universe may not be fated for eternal acceleration. Its future could hold surprises beyond imagination. If modified gravity theories are supported, then the very framework of space-time would need rewriting, and Einstein's century-old equations would give way to something new. And yet, no matter how advanced these tools become, there will always remain a horizon, a boundary beyond which no information can ever reach us. The cosmos will always keep some of its secrets, locked beyond the limits of light and time. But that is what drives the effort forward. Each new mission, each new telescope, is a step closer to the ultimate question. Not merely how the universe expands, but why it exists at all. The story of expansion is still being written, by golden mirrors floating in the darkness, by silent observatories under the desert sky, by detectors that tremble with the faintest ripples of space-time. They are humanity's instruments of wonder, listening to the cosmos as it continues its great unfolding, measuring the rhythm of a universe that will never stop growing. In the quiet of reflection, the question returns, older and deeper than before. What does it mean for a universe to expand when there is no outside for it to fill? Perhaps the question itself carries a flaw, a relic of the human mind shaped by life in a bounded world, where every path leads somewhere, where every horizon hides another shore. For billions of years, the cosmos has grown without edge or border, its expansion not a movement into space, but a transformation of space itself. There is no destination. There is only the continuous act of becoming. This is the image modern cosmology leaves us with, a reality that is self-creating, a stage that writes itself as the play unfolds. Every moment births more moments. Every stretch of space births more space. The universe is not so much going anywhere as it is making more of itself, weaving an ever larger tapestry from threads of time and energy. This vision carries with it a subtle kind of awe, for it means there may never have been an outside at all. The universe is not surrounded by anything, not floating in some higher void. It is the totality. To ask what lies beyond it is like asking what lies north of the North Pole. The question itself dissolves when followed to its end. And yet the human mind resists this answer. It continues to search for an edge, a final frame, a place from which to see it all at once. This longing is not an error, but a testament to our nature. We are the only known creatures who look outward and imagine a beyond. We draw maps, chart stars, and write stories that carry us past the horizon. And so, when cosmology tells us that there is no beyond, the result is not despair, but wonder. For it means that we truly exist inside the only reality there is, with no veil left to lift, no curtain to pull aside. Some philosophers have suggested that expansion is not into space, but into possibility, that the universe is exploring the range of what it can be, creating new configurations of matter, new landscapes of time, new chances for consciousness to awaken and look back upon it. In this sense, expansion is not merely a growth of size, but a deepening of being. If this is true, then every galaxy drifting farther from another is not a sign of separation, but of creation. Every new cubic light-year of space is a blank page on which the universe writes another line of its story. The accelerating expansion becomes not an escape, but an unfolding, a way of stretching the narrative forward, pulling existence toward futures yet unimagined. Perhaps this is why the idea feels so hauntingly beautiful, because in it, we find a mirror for ourselves. Humanity too expands, not outward into new lands as much as inward into new understanding. Each generation pushes the edge of knowledge farther, asking questions that their predecessors could not imagine. And though the answers may lead to deeper mysteries, the search itself is what gives the journey meaning. Seen this way, the universe's growth is not a race into emptiness, but a slow flowering. It is as though reality is leaning forward into its own potential, testing the range of its own imagination. Galaxies drift apart, stars are born and die, planets arise and vanish, and on one small world, a thinking creature dares to ask what it all means. Perhaps the greatest revelation is that we are not standing outside this process, looking on. We are woven into it, as much a part of cosmic expansion as the galaxies themselves. Every breath taken, every thought formed, every question asked, all of it belongs to the same unfolding. The universe grows, and in some quiet way, we grow with it. And so, the final image is not of a balloon rushing into emptiness, but of a story writing itself from the inside out. The expansion may not be outward at all. It may be inward, toward ever deeper levels of complexity, consciousness, and wonder. The cosmos may not be fleeing from some imagined center, but spiraling inward to the heart of its own meaning. And there, somewhere in that meaning, is this moment, a fleeting interval when the universe paused to look at itself through human eyes and asked, "Where am I going?" The answer may never be fully known, but perhaps the asking is enough.